audio. So hopefully few seconds perhaps. Yes. Is it working? I'll turn it off once. Okay. Alright. So, thank you all for joining. It's a pleasure to have Harshan Jagadish from IIT Delhi giving this talk. He's currently an assistant professor in the Department of Electrical Engineering at IIT Delhi. He did his PhD from ECE, the Indian Institute of Science, Bangalore. Before joining IIT Delhi, he spent some time in Singapore with the cybersecurity group at the Advanced Digital Sciences Center. He also did postdocs at NTU as well as Monash, and he's broadly interested in information theory, security, wireless networks, and applications of information theory encoding to communications and storage. So today he'll be talking about a list-based approach for optimal ARQ distribution problem in multi-hop networks. So again, over to you, Harshan. So Harshan, a couple of other questions. So you're always assuming that this is a line network, right? From the source to the destination. It's a line network. A line network. So so there's only one path from the source to the destination, right? Yes. Yes. Sure. Okay. Alright. So the other thing is, how does the number of relays scale? So is it typically a constant, or is it comparable to the block length that you're interested in? Okay. Thanks. So, and the feedback is just repeat. That's the only feedback is repeat request. That's it, right? Nothing else. Okay. Right. Right. So the error correcting code will have to have an error detection mechanism to request for retranslation, right? Okay. Okay. Sure. Yeah. Yeah. Thanks. Harshan? Hi, sorry to interrupt, Shashank here. Yeah, so if I understand correctly, if all the channels are identically distributed, then you will uniformly allot the same number of retransmissions for each, maximum allowed retransmission for each. Okay. Okay, sure. Okay, so you're actually, so the goal now is to, depending on the channel statistics, to find the optimal distribution of the queues, Q1, Q2, Q3, with sum to Q sum, right? Okay. Yeah. Okay, thanks. Is it still there? Okay, because I don't hear any issue. Okay. You can't hear him speak? Ah. Am I audible? Hello? Check. Check.
Nobody knows how many retransmissions are allotted to the previous or the next succeeding nodes, but all that they do is they will wait for the packet from the previous node. If they're able to successfully decode it, then they will forward it to the next node. Now, if they're unable to decode, then they will send out a retransmission. Now, this node doesn't know whether the preceding node had a sufficient number of retransmissions, correct? So it will just wait for some amount of time. So that's a part of the protocol. Now, even beyond this time, if it doesn't get any packet from the previous node, then it thinks that, you know, this particular node has exhausted its number of retransmissions. But that's the way to implement this particular scheme. All right. So that's what is called as the non-cooperative ARQ strategy. Now I'm using the word non-cooperative here because there is no room for making use of any unused attempts from the previous or the preceding nodes. Okay. So this will be clearer in the subsequent slides. Now, let's just take an example of how this particular method works. Now, we are just looking at the case of a success. Success meaning one such event where the packet reaches the destination. So again, let's see the color convention here. So every node has 2 attempts allotted to it. Okay. Now, that's okay. But then once the packet goes to relay 1, the relay 1 will have to use the number of attempts given to it, which is just 2 of them. Okay. Now, because, you know, it doesn't know how many ARQs were allotted to the other nodes. Now, what does relay 1 do? So what it does is it will perhaps, you know, start with the first one from the bottom. Now the red implies that it was unable to communicate with that particular code word, right? Then because this was a failure, it uses its second attempt, and then luckily this second attempt was a pass, and then it actually got to the second relay. And then what happened then? Relay 2 in its first attempt somehow saw a success, and then, you know, finally the packet went to the destination, right? So this is one scenario where the packet reached a destination, but no, this is basically the profile of usage of the ARQs allotted. Now, if you carefully observe this particular attempt, which was unused by the source, it basically went waste because, you know, because relay 1 did not have any information related to that. So, you know, all that it had was just 2 uses, okay, or two attempts, and then somehow it was able to make use of one of them to succeed. So everything went well. But then, you know, there could be some not so good cases, right? So for example, let's take a look at the failure. Okay, here this is one such instance. Everything went well with the source because its very first attempt it was able to communicate. Now the second attempt was not needed because Now what happened to the relay? Now this relay had 2 ARQs allotted to it. It did not know the ARQs allotted to the source. So then, you know, unfortunately, the link between relay 1 and relay 2 was pretty bad. And even after using 2 attempts, it could not forward the packet to relay 2, right? So it could not do much. So the packet really got dropped here. Okay. So then, you know, there's no use of saving in on one ARQ here. And also we had given 2 ARQs to relay 2. Even that did not really get utilized because of the non-cooperative strategy, because, you know, every node was asked to use only the number of retransmissions allotted to it. So it tried its best to communicate within that, and then, you know, in this particular scenario it could not communicate, right? So this is basically the feature of the non-cooperative strategy. Okay, now this is just an instance where the packet gets dropped here, but then, as I said in the past, it could also get dropped here, or anywhere here. And then if you want to think of how to understand the PDP, we can nicely write an expression for that. Okay, and that particular expression is actually what is given here. Now, what is this? This is the expression for the packet drop probability for the non-cooperative strategy. Now, as you can see here, it is composed of the events wherein the packet gets dropped at multiple links. For example, if you look at P1 power Q1, this is the probability that the packet gets dropped at the very first link, because suppose if it gets dropped here, that means both these cases or both these attempts must be failure, right? And then if you assume that the channel statistics were independent between the two, then then that gets just multiplied by P1 as many number of times, right? So P1 is some sort of a you can think of it as a probability expression of failure of that particular attempt. And then assuming that channel realizations are independent, P1 power Q1 is the probability with which it gets dropped here. Okay, and that's one such event. Now, it could also happen that the packet could get dropped in the second link. Now, if it has to get dropped in the second link, now the second link must exhaust all its attempts, and that's basically given by P2 power Q2, right? But then it cannot be there hanging there without any support, because if the packet is getting dropped at the second link, then there must be an accompanied probability with which the packet has survived. Okay, and that basically is the next set of terms. For example, with the second link, we would just have a 1 minus p something, right? So that's basically the complement probability with which the packet made it through the first link, and then it got dropped in the second link, right? And likewise, if you expand this particular term, it's like somehow the packet made it to the 3 links and then got dropped in the 4th link, and then it made it through a 4th link and then dropped in the 5th link, and so on, right? So we can nicely write down this type of an expression for the PDP, and that's basically incorporating the protocol into the consideration. And once we do it, what do we have? So we have an objective function, right? So we can write down the problem as given here. That's basically, let us minimize this PD over the variables Q1, Q2 to Q1, subject to the constraint that each value is strictly more than or equal to 1, because everybody needs to get at least 1, because they don't know how many ARQs are given to the other nodes. So at least it needs 1 transmission, right? And then naturally these are positive integers, and they all must sum up to Q sum. So the entire problem is posed once Q sum is known, and then once the long-term channel characteristics are known. So what I mean by that is the values of P1, P2, P3, and so on, they are already known, because that's a direct relation with the long-term channel characteristics. And once that is known, then the entire problem formulation is only based on the variables Q1, Q2 to Q1. Okay. So is the problem formulation fine? If you have any questions, I can take it up here.
Yeah, Harshan, just Amitalok here. Just one question. So QSUM is a parameter which is fixed upfront, right? This is the total budget available upfront.
Correct. That's right.
Okay.
And that's how we are able. Now we are asking it to distribute, and as Shashank mentioned, intuition tells us that if the link qualities are identical, then maybe the best idea is to just divide this QSUM uniformly among all the links, right? But then in general, because these links are heterogeneous, the optimal way to do it is perhaps could be different, could be other than uniform distribution. Okay. Now, the solution to this particular optimization problem, we are going to call it the optimal distribution. Okay, because that's the one that minimizes it. Now, how do we approach this particular problem? We will have to look at.
Harshan, sorry to interrupt. Amitalok here again, but there's a question by Vinay Kumar. So his question is: change of protocol changes the expression of PZ. Is that correct?
That's true.
Okay. Yeah.
That's true. So as I mentioned, we are only looking at the non-cooperative strategy, and we will soon see that as for different protocols, the PD is going to be different, and therefore the corresponding optimization problem and their approaches will change.
Okay. I hope that answers. Yeah, he says thank you. Yeah, please proceed.
Thank you.
Yeah.
Right?
So Harshan, one more question. Shashank here. So does this? I mean, is the assumption that you are using decode and forward particularly important? So everything basically seems to boil down to using an ARQ scheme, right? And if, I mean, so for example, you could use an amplify and forward scheme, but you could have a retransmission if that particular link went to a deep fade, for instance, right?
Right.
And basically the same expressions would hold, except that the values of the PIs would be different as well.
Again, it is still a function of many other things. So it depends on how does the destination decode. It could possibly get multiple copies, and all these copies are now soft values because you would be doing an amplify and forward, and then once it gets soft copies, then whether it combines it in a soft manner or how it decodes. So it's all dependent on that as well. Does that answer your question?
Sure. Thanks.
Okay, thank you. So, so here we are staring at an optimization problem, and I mean, for anybody who looks at an optimization problem, the questions that arise are like, first of all, does this have a single minima? We call it as a global minima, or or does it have multiple local minima? That's one thing, and the second thing is how do I really solve this particular problem, and how do I approach? How do I get that local minima from this? And so on. And then, is there an algorithm? Are there guarantees that, we are always able to obtain the best result and so on? Okay. And as we know, that's mostly dependent on the objective function and the constraints, right? But now, to take a look at this particular problem, this is on a discrete space because the variables q1 to q1 are themselves positive integers and they are bounded. So you can think about the search space as because they are bounded in terms of something like a box, right? And then it's not a continuous space, first of all, and then moreover the function is also we cannot say anything about its convexity or anything because basically that doesn't hold anymore because of the discrete nature of the problem. So we would need to think about some way to solve such problems. And given that we are looking at finite numbers, or rather the bounded ones, one thing is clear that the search space for exhaustive search is bounded, right? Because there is some constraint on each of these numbers, q1 to q2 to q1, and then individually these numbers are also non-negative. So they are greater than or equal to 1. So which means there are not infinite number of candidates for testing or getting the best solution. Okay, but then this is not what we want. We don't want to really do an exhaustive search because, as we know, that doesn't scale well with either the parameter q sum or the number of hops in the network. In particular, what we have seen is that the exhaustive search complexity, or rather the total number of candidates in the entire search space, is q sum minus 1 choose n minus 1, right? So that's the order with which it grows, and we really cannot think of solving the problem this way. Okay, now of course it still because these are all bounded numbers. Definitely what we can do is we can take out some time and then implement exhaustive search, and then at least that will tell us this is the best one can do. And then once we have a low complexity algorithm to solve the problem, at least it gives us a baseline or a benchmark that whether we are closer to the optimal solution or not. So that's the benefit of having a problem on this type of a space where the number of candidates is bounded in size and they're all discrete. Okay, so alternatives, we somehow need to work on the characterization of the objective function, understand how this function behaves over different values of q and q2, and see whether we can comment on its shape and something like that, so that we can go to the local minimas in a fairly straightforward manner. And if possible, this is a standard way of thinking of solving any optimization problem, is you have to look for equivalent problems. Okay, so the objective function need not be the same, but then if you can show that you take up another problem, solving problem 2 will help you get a solution for problem 1. This type of an equivalence, if we can come up with, then that would also be helpful. And combination of these two, why should we only want to look at the local minima or the global minima, right? So if I'm somehow able to come up with a list which is around the minima, right? So suppose there is a local minima, right? I don't want to really get the local minima directly, but somehow if I can identify a patch of candidates in the search space, this is not the entire search space, but a very small patch, and that patch, if it contains the local minima, then I think I'm still good, because the way in which we identify the patch, if it is of low complexity, then once I do that, then the rest of the task is that I can probably exhaustively compute among those candidates, and then get the one that is the minimum in PD, right? So it's not exhaustive search, but it's like a list based algorithm. So you identify the list, but then ensure that the list is identified with low complexity, right? And if that is done, and if the list size is small, then maybe that's also not a bad idea to solve such problems. Okay, so these are the alternatives that we should be looking at, and this is what it exactly leads us to finding out something strong in terms of, or concrete in theory. Okay, so with this we will be moving into a few theoretical results on this particular problem, and I have listed a few results. As far as possible, I will try to give you some intuition on why these results are correct, and then why are these intuitive. Okay, so let's look at one of the first results for this particular problem. Now, again, these are all analytical observations on the objective function. Now, the first result is that for this network, the PDP that we have, which is the formula that we had in a few slides back, what we are claiming is that this is invariant to the permutation of the links. Okay, so what it means is, I start with a network which had like C1, C2, C3, C4, and so on. This is basically the order which is as dictated by the physical network. Okay. Now, for this network, I can compute the PDP of it using the formula. Now, what we're trying to say here is that even if you come up with any random permutation of this network, so I could possibly have the second link in the first place and the first link in the fourth place and so on. Any possible permutation of these links, then you're going to construct a new channel, which is not a physical channel, but it's a virtual channel, right? Now, on this particular virtual channel, if you compute the PDP expression, then we are claiming that it's going to be identical. Okay, so that means the objective function is invariant of the order of the CI values. Okay, now how do we prove it? One intuition here is that if you look at it, the number of retransmissions is only dependent on that link, because everybody uses their retransmissions as allotted to them. Okay, so when you are permuting the network to construct a virtual network, you are basically copy pasting the node and its forward link to somewhere else. Okay, so, and because these nodes, they don't really make use of any information either from the past or to the future, it doesn't really affect anything, because we are moving the node and the forward link along with it and to some other position. So that's the intuition that it should not change. And then formally we can prove it using induction and then in a concrete way. For example, if you are looking at a very simple example of a two-hop network, which is as shown here, then the special case of the packet drop probability would be like P1 power Q1. This is the probability with which it gets dropped at the first link, and then the probability that it gets dropped at the second link. That's the union of the two, right? So this is the expression for it. Now, if you swap it, then you basically take this C2 Q2, okay, and then the color coding is not all right here, but then if you take C2 Q2 first, and then if you put C1 Q1 later, then the expression for this particular virtual network would be P2 power Q2 plus this expression. But then, after a small modification, minor modification, you see that these two expressions are the same, right? And this actually forms the basic step of induction. And then we can continue further and then say that, we can assume that this particular thing is true for arbitrary k-hop network. And then we apply the usual induction step to prove that it is true for k plus 1. And that's fairly straightforward. But the point is the intuition. The intuition is that, the non-cooperative strategy, wherein they don't make use of any of the information related to ARQs to the previous links, as well as the succeeding links, and that what makes it the fact that if you permute it in any manner, the overall PDP is going to be the same. Okay, so I'm not going to get into the entire induction proof, but that's basically the intuition, and it's easy to compute the rest, complete the rest of the steps in the induction. Okay, so this is one property. So it's like you keep identifying some nice properties of the objective function, and then finally collate everything, and then think of a solution to a low complexity solution to solve the problem. So that's basically the approach that we have taken. So we are done with one result. Now what else? Now we have one more result. What it says is that under some conditions on the channel characteristics, so you don't have to pay a lot of attention to the first line here. And what it says is whenever we have a link which is better compared to another link, for example, as I had mentioned, this CI is the parameter that captures the quality of the link. So if CI is more than CJ, then what it means is the number of ARQs that must be given to the good channel should always be less than the bad channel. Okay, so this is some reminiscent of this type of a water filling type of an idea, right? Whenever you have it's in fact contrary to in fact it's against that. So whenever you have a good channel, the good channel must actually not be getting more ARQs than a bad channel. Okay, now this is again something that can be done using induction, but the intuition here is that if the channel is already good, then you should possibly give more number of attempts to a poorer channel compared to itself, right? So that's basically the intuition, and we can also prove it formally in the following way. So in order to prove this, we will have to make use of the permutation result from the previous theorem. Now, what it means is when we are focusing on a given pair of channels, because this is where we want to figure out who should they get more ARQs or less ARQs compared to the other one, right? So basically we want to ask this question by fixing any two channels. Now, suppose, let's say I want to answer this particular question between, let's say, the first link and the second link here. Okay. Now, I don't want to disturb the rest of the link as it is, rest of the network as it is, but only want to address what happens to this particular case. Now, I invoke the results of theorem 1, and to do that, we need to say that the PDP of the entire network is invariant to permutations. So because it's invariant to permutation, what I can do is I can bring these two channels of interest to the end of the network. Okay, you keep introducing shifts and then come up with a permutation wherein you have brought in this C1 and C2, these two links, to the last two links of the network, and then you just push back the rest of them into the first part of the network. Okay, it's a virtual network. That's fine. Then we know that the PDP of the network doesn't change. And once we do that, we can ask questions related to what to do with the allocation for only allocation between this link and this link. Okay. In order to do that, we don't worry about the first set of links, because in the PDP expression, this actually comes out as a constant. And then, we can only take this as a common and then only look at these two particular links. And in order to prove this result, what we do is we assume that both these links have the same number of ARQs to start with. Okay. And then the question is, given that the C1 is more than C2, the question is, let's say I have one more ARQ with me, and then should I really give it to C1 or should I give it to C2? Okay. And then if you pose that question, then we can actually obtain two hypotheses, either giving it to this or this, and then we can show that one of the hypotheses always can be chosen. Okay. And in order to do that, we will have to make use of some computations and then show that the PDP that you obtain in one case is always going to be less compared to the PDP in the other case. Okay, which will bring us to the conclusion that when you have a good channel, or when you have a poor channel, right? So the good channel must not get more ARQs than the poor channel. Okay, so that's the result coming in from this. Now, I've given you a gist of how to do this, but then this basically makes use of induction step and swapping of results coming from the previous result. Okay, so what we have done is we have accumulated two results, and we have some understanding on how the objective function is, and then how should be the ARQ allocation done, at least when you're looking at two links at a time. Okay, so any questions on this so far?
I guess no. At least I don't have any questions. I guess yeah. So there's nothing in the YouTube live stream also. So yeah, I think we can go ahead.
Okay, thank you. Thank you. So with these two results, we will proceed further and see if there are other interesting characteristics of this particular objective function. Now, even before going to anything further, we first need to design or decide on what we want, right? So we want to look for a local minima in this particular search space. So I'm going to call this search space as yes. Okay, and this is basically bounded in size because of the discrete nature, and then the bound on q sum. Now I'm going to call a distribution. This is a vector basically. It's like q1 to q2 to all the way to qn, and this vector I'm going to call it a local minima if it satisfies the following properties. Now what is this property? Basically, if you look at a vector and then if you want to call it a local minima, you look at its neighbors. Okay, where are the neighbors? The neighbors are basically in this search space. And then how do I define a neighbor? Now the nearest neighbor is the one, we'll say that it is the one that differs by Hamming distance 2. Okay, and why is it Hamming distance 2 and why not 1? For example, you take a look at this particular vector q1 q2 all the way till qn, right? Now if in one position there is a difference, let's say they differ by 1. Okay, now it cannot be the case because even its neighbor must also satisfy the sum constraint because they all must add up to q sum, right? So on one location, if it is short by 1, that has to be correctly compensated in the other location. Okay, which means in a different location, this should be compensated, there should be a change. And what it means is the minimum Hamming distance between these two vectors is actually equal to 2. Okay, and these are going to be my neighbors. Okay, so now when we have a vector and then we are looking at all possible neighbors, then if you evaluate the PDP on all the neighbors, the PDP of the neighbors must be greater than or equal to the particular point. Okay, and only then we are going to call it as local minima, right? So that's basically the geometric representation of what local minima is. Okay, but based on the neighbor definition, we can see that this particular vector can differ from its neighbors in any two positions. Okay, so let's call it, let's say I or j. Okay, so I think there's a typo here. I think this one of them has to be a j. So let's say this is qi, this is all right, but this must be, let's say, qj because I and j have to be different. Okay, now there are, like, you can choose any two positions in this particular vector, and then once you choose a position, these two positions, then you can have a -1 on one and the plus on the other. That gives us one neighbor, and the other neighbor would be like a +1 on the first one and then the -1 on the other. Okay, so overall we have about roughly 2 times n choose 2 neighbors at most, which can be possible around a given point. Okay, and if we can show that the PDP evaluated around the neighbors is strictly more than or equal to the corresponding point, we are going to call it as the local minima, right? So that's the definition of a local minima. Now, just as an example here, there is a plot for just in 2 dimension. The Q1 and Q2 are these two values, and then these are possibly the candidates for a given Q sum of 8. Right, so we can list them this way, and then the neighbors of 4,4 are just going to be 3,5 and 5,3 because that's there needs to be 2 of them because in this particular case they differ in both the index values. Okay, that's just a simple picture for the 2-dimension case. Now, what is that we do? What we will do is, by making use of this local minima now, and especially the fact that the neighbors behave in this way, what I can do is I can compute the PDP of Q star, okay? And then I will come up with a condition on when is this going to be less than or equal to its neighbor. Now, its neighbor is going to be of the form, everything is same. The only difference is that on 2 locations, it just differs by 1 on the minus side and the other one on the plus side, okay? And what it means is, again, by making use of the permutation theorem, you can focus on those 2 index values that are differing, and then you can bring these 2 index values to the end of the vector, and then you can put the rest of the components on the first portion of the wireless network, on the network, and in which case you can actually be able to compare the PDP of one expression with respect to the other, and then probably make some inference on the comparison between the two. Okay, so if we take up that particular approach, we have in fact shown that a vector q star is going to be a local minima if and only if it satisfies this type of an ugly relation. Okay, I mean, at this point it looks a bit ugly because indeed it doesn't look very simple. We will soon see that this can be simplified eventually. Okay, now it's an if and only if, which means both the directions can be proved. And I'm not going to get into the details of this particular theorem, but we'll try to make some inference using this particular result. Okay, now what we can see is that when the links, or let's say the signal to noise ratio of every link, is relatively good or sufficiently large, we can actually show that this first term of this expression actually goes down to zero. And that happens because of if you look at each of these expressions, this is like a geometric series, like 1 plus p power something and so on, right? And then at very high, at high SNR values, each of these p values are very small. And then when you raise it to the power of several numbers, and then finally it also dies down. And then the only thing that you would be left with is the term like of the form pi power 0. Okay, and that's actually equal to 1. So when the SNR is good, then you have a 1 getting dominant here, you have a 1 at the bottom as well, and then this would be like sort of a log 1, and then this will go down to 0. Okay, likewise you can also show that the first term of the second expression will also be very close to 0 when the SNR is good. And this basically makes the if and only if condition very simple. Okay, and all that it says is that the optimal ARQ distribution is in such a way that if you look at its ratio, it is indeed related to the logarithm of the corresponding values of the probabilities. Okay, just discard this particular term in both these expressions, and then again, if you also bring in this particular relation into picture. Okay, now if you bring in this relation, this particular ratio is going to be sandwiching in between these two, and in addition, if you also have these put together in appropriate order, it can actually be shown that the optimal condition, or the condition for the local minima would be actually satisfying the equation shown at the bottom of this particular slide. Okay, so with all the results that we have, we are able to arrive at some relation on the local minima by using some relation with the values of PIs and PGs. Okay, so any questions?
So maybe so here, I mean, it still doesn't tell us how if this is efficiently solvable, right? I mean, or if so for example, how would like heuristic algorithms? I mean, for example, you could do a convex relaxation of the integer program that you have, or I mean, there are also other heuristic methods like this taboo search, simulated annealing, and all of those techniques, right? So,
Right.
so I mean, as a first try, would that give something reasonably good?
Yeah, so in fact, we did not go with those attempts because when we started with some characterization of these functions, we were able to figure out the solution, right? So given that this is fairly straightforward to implement, which is just inverse is just O of n cube of complexity, we would want to go ahead with this and then suggest some modifications into the solution so that we end up with a good solution most of the times. And what do we do? So the flow chart is as given here. So we first compute the constants. Now this is basically the ratios of logs. So I think this must be a typo here, right? So it's log of, this must be logarithm here. And then once we get this, we solve the system of linear equations, and then we'll get a solution in the real space. Now in the real space, so the trick is we have to sort of round these values somehow. And then what we have done is we have suggested to sort of seal these values into the nearest integers, which are more than them. And then once we have it, now we get a candidate solution in the search space, and these are all integer values. Okay, of course, but there could be some perhaps that has to do with the approach that we take of reverse engineering. because once we saw QSUM, then we just looked at a deterministic way of distributing it. We didn't really think about fitting any need for fitting a probability distribution on the usage of ARQs. So we didn't think about it. Yeah. And again, the second one is what? The list? I did not get the second one again, sorry.
The second one is he says, just thinking of high probability results. I think he just commented. I think that your question, your answer has been basically has addressed his query most likely. Yeah, he just says that's all. Yeah, I think you addressed that question. Thanks.
Okay, thank you.
Yeah, actually, I'm sorry. I kind of hogged over the moderating roles. It's Shashank's thing, so sorry about that, Shashank. Please continue.
No worries. Thanks a lot. Any other questions? I think Lalitha wanted to ask something.
Just a quick question. I mean, it's like it's a very. I mean, just looking at your expressions and perhaps, there was one place where you were using swapping, and at some other place where I see, integers relating to log of probabilities. I'm just reminded of the Huffman algorithm, and which does this integer optimization. But then, maybe it's not even close. But it just reminded me of that. I don't know if there is any far relation at all or not.
Okay. Okay. Yeah, that makes sense. So somehow, we did not really look into any such connections. That's
Yeah.
yeah. So we were sort of too focused on looking at this as a standalone problem. So
Right.
yeah.
Right.
So maybe I'll take a look at it, and then if I see some strong connection, that would be a great thing to know.
Sure.
Yeah. So just to continue, I think this. Yeah, so we have log, and this log is not to base 2. So it's not about representation of a random variable. So that's the main difference here. But still, you don't know. So right, yeah. It's not log to base 2. So the log appears for totally different reason.
Yeah. So I mean, I know the problems are very different, but at least they are both constraint and integer optimization problems. And yeah.
Okay, yeah, I agree with you.
Yeah, thanks, Lavita. Any other questions? I guess no questions from the live stream as well. Okay, so thanks again, Harshan, for kindly agreeing to give a talk on theory matters. I mean, it was really interesting. I mean, we would have loved to hear more about the other strategies that you have, but I guess the cooperative strategies would perhaps perform far better than the non-cooperative strategy, I guess, right?
It does, precisely, exactly. So because as we saw, the non-cooperative strategies, they don't really make use of the unused attempts. So,
yeah, exactly. And I guess if the number of hops is fairly large, then I presume that there'll be a large number of unused ARQ budget that's left over.
that's true. And then, in fact, they outperform remarkably. So it's a huge benefit in adding it, in building this cooperation. But then, from an implementation point of view, that would also require some amount of coordination.
True.
So it's a decision that needs to be made judiciously between the overhead for implementation and the gain that we get out of coordination.
Yeah. Okay. So yeah, thanks again, Harshan. I will stop the live stream.
Yeah.